Ladies and gentlemen, dear colleagues, the paper which I will present in front of authors Zoran Stevanovic, me and Sasha Milanovic is Karst aquifer as a buffer for climate variation and changes. On the first place to underline, but I think that several of us mentioned during last day and this morning, that around 20 to 25% of world's population consumes groundwater originating from karst aquifer. The similar situation exists in Southeast Europe and in Balkan too as well. In terms of the proportion of karst water in its water supply system, Austria with over 50% is the leader. The homeland of classical karst is Mesozoic carbonites. Along with alluvial groundwater and surface water from the reservoirs, the water from the karstic springs is the main source of water supply in the region, in these kind of regions. Tapping large springs is the traditional method of water supply in the region, but the main concern is their unstable discharge regime. About that will be talk a little bit later. Here is the same figure like Zoran showed that this is area of karstic area in Southeast Europe, and some main springs are presented on this figure. Now just to remind you that we all learned from Roman time experience that they used 11 long aqueducts for delivering more than 13 cubic meter per second of water to Rome, from distance ranging from almost 100 kilometers. Several water supply systems from that time are completely reconstructed and still in use the same, they are still using the same springs and pipeline roads. Now, just to mention that several large cities in Southeast Europe with populations of over 500,000 that depend on karst aquifers and their discharge regimes. Among them, five are capitals: Vienna, which Zoran mentioned, Tirana, Skopje, Sarajevo, and Podgorica, and some of, like Banatska Bystrica, Niš, Krajova, Konstanca, Thessaloniki, which are not capitals, but still big cities, use only karstic water, or in case of inefficient discharge, combine them with water from other sources. About Thessaloniki, Zoran already shown the situation. Now, just to mention Vienna water supply. Vienna water supply system is very, very old, more than 130 years, or even more than 130, and it consists of two major gravity pipelines. One is 150 and second one is 180 kilometer long. Detail I will not here is explained. Here is photos of Kaiserbrunn spring, the spring which Vienna using more than 130 years for their supplies. It's one of more than 20 karst springs which they're using for water supply. Now, Sarajevo using group springs, actually, Vrelo, Bosne springs, which drain rich Triassic aquifer from Igman mountain, and the range from minimum to maximum is 1.4 to 24 cubic meter per second. What is with Podgorica? Actually, with Montenegro and Podgorica, they using acidenting springs which appear in contact of limestones and fluvial glacial sediments. They are pure. They're using actually pure water, and they need only chlorination and after that for water supply. Tirana using three karst springs, Selita, Šemrija, and Buvila. This groundwater is with low mineralization and very good quality. Natural conditions and unpopulated catchments are in favor of sanitary protection. Skopje as well using Karst spring, which is situated on Vardar river bank, upstream of the town. And discharge regime is relatively stable. The mean flow is around 2.5 cubic meter per second. Now situation with karst aquifers in Serbia. Dinaric and Carpathian karst sources provide about 35% of drinking water to the population in western and eastern part of our country. The largest springs are mentioned Mlava, always mentioned Mlava. I will tell you later why. Minimum and maximum discharge is 0.3 to 14, and second one is Perovčac, which drains on the west. Mlava is on the east, and ratio is 1.3, 6.2 cubic meter per second. What is with problems along the coast? Adriatic and Ionian coastal tourist areas strongly depend on groundwater from the karst. Besides the problem of karst shortage during the recession period, summer, autumn, water pollution or salty water intrusions often means that local water and economy sectors cannot be expanded and properly developed. Some of very important springs for supplying some cities in Croatia is Jadro, Split, Ombla, Dubrovnik, etc. What is with Montenegro? Here is some photos which shows during wet and during dry season, and I have to underline that minimum ratio between minimum and maximum is sometimes 1 to more than 100,000. Some more photos from Montenegro. Now, main advantages and disadvantages of typing karst aquifers. First advantage is the exploration of karst groundwater is more costly and less predictable in terms of final outcomes, but the exploration is regularly much cheaper and environmentally friendly than surface water use. Second disadvantage, due to the unstable regime of the karst source, the main problem for most of the waterworks is to issue water supply during recession periods, during summer, during dry period when we need desperately water. Now karst is a buffer. The importance of karst is a reflection in the ability of karst massifs to accumulate a certain water quality and to realize it subsequently through karst springs. Karst could amortize the effects of huge and intensive hard rainfalls. Areas could be large, reduce the impacts of floods. On the other hand, large static reserves that can largely help bridge to problematic rainless periods, dry periods during summer, are often formed in karst. These reserves are easily recoverable in periods of high precipitation. Such an advantage has been applied in several successfully implemented regulation projects in Serbia, which was done. And finally, the advantage of underground accumulation formed in karst in that the expected, predicted increase in temperature, which with the all scenario predicted, will not stimulate evaporation from these accumulations. This is very important. Now, first example, Baseflow, ecological flow for dependent ecosystem guaranteed by karst. Again, Mlava spring. Why Mlava spring? Always Mlava spring. This is one of the largest karst spring in Serbia. Okay, this is first. Second, this is Piti, still not tapered, and it is very potential for regional water supply. And second, very important, because this is observed well. We start with observation of discharge of karst spring since 1966. That means daily observation, of course, that we still have long period and we can play with data to analyze everything what is important for some projects or some idea. Mlava drain northeastern part of Beljanica, Karst Massive, and catchment area is around 100 square kilo, 125 exactly. Not exactly, but around. Downstreams, we have two gouging station, hydrologic station. First is Gornjak station, control catchment area around 600. Percentage of karst terrains which control this station is around 35. Second one, downstream of karst spring Mlava is Rašanac. 10 times higher catchment area controls, but that means around 1,000 square kilometer, and only 70% belongs to karst terrain. Here is a graph for 1984, it doesn't matter here, but just to show what's going on. This is free discharges, free hydrographs. Gouging station Rašanac controls catchment area 2 times bigger, higher, larger than Gornjak, but during summer months the peaks are almost the same. Now, during dry periods, summer, autumn, the quantities of water starches registered in all 3 sections are almost the same. 10 times higher catchment area controls Rašanac, just to underline again. Now, just relation between catchment areas, 10, 5, 1, and in dry periods, just relation of discharge, 2.3, 2.2, 1. This shows that the base flow of Mlava Rašanac at downstream profiles Gornjak and Rašanac almost exclusively comes from the karst aquifer, and that the ecological flow strongly depends on karst spring discharges. Now, second example, again, we used Mlava spring. The catchment area of Mlava spring is characterized by the much larger values of specific yield than the other 2 areas, the specific yield in 2 times greater than calculated value of downstream gouging station Gornjak. And the same situation is in dry period. Here is table which shows catchment area, percentage of karst, discharge, runoff on that 3 stations, and specific discharge and ratio during year and mentioned year and dry period. Now that Mlava, karst aquifer has potential to provide sufficient water for different kinds of consumers, water supply, etc., adequate regulation measures and management would be necessary during expected longer dry periods. Now, third example, we used for third example a Lužnica river flow regime, and this was taken as an example to demonstrate the effects of amortizing flood waves in karst. The confluence of Lužnica river into the Vlasina river is in town Svođe. There exist 2 stations on these 2 rivers and before confluence. Now, hydrographs of these 2 rivers, blue line is Lužnica, red line is Vlasina river. What is important? Important that both catchment area are the similar size, around 340, something like this, and they have, because they are in neighborhood, similar pluvographic regime. The peaks are smaller in case of Lužnica hydrograph because of more significant infiltration into the karst rocks. Infiltrated water were retained in aquifer for a certain period of time, sufficient to prevent flood effects. This is not case with Vlasina river, which drain most known karst area. Now, delaying of discharge in karst. Karst aquifer system often discharge water with some delay. Resistance time can be from only a few days to several weeks, even longer, depend on actual saturation and storativity. The buffering effect sometimes enables the management of stored waters. This could be a great importance during dry periods, which are likely to be more frequent in which are expected in future. Here is shown delaying. Red line shows stream flows from the catchment, which consists mostly of low to semi-permeability rocks, non-karst, and the blue line is which control karst area. Delaying of several days is shown. The above examples, which I mentioned several, 4 I think, indicate the importance of karst aquifer in terms of its high porosity and storativity. In contrast, of course, when carbonate rocks are slightly karstified, groundwater reserves can be very small or limited. Certain parts of, the time going. In this case, drainage behavior can be very similar to non-karst or this different kind. One example is rapid propagation of rainfall. Ishka River period from during 3 days fell around 500 millimeter. After that 3 days rain, propagation through the karst formation caused a massive flood wave around 60 cubic meter per second. Here is hydrograph and river bed. The reaction of aquifer to intensive rainfall after a long dry period, the fast increase of groundwater table usually indicates limited storage. A jump of almost 50 meters after only 24 hours of intensive rains, hard rains, it's known from eastern Herzegovina. The typical example of fast replenishment and appearance of temporary spring, which is drainage formation in northern Iraq. Here is hydrograph and temporarily active spring photo. Better understanding of karst and assessment of stored groundwater reserves are particularly important where the negative impact of climate change is concerned. Some preliminary calculation for indicates abundant reserves in karst massive, Beljanica, Kučaj, Vidlić, Pešter, etc. have to be verified and these areas protected and preserved like alternative source for a future for water supply in Serbia. Regulation is important in karst for all these things which I mentioned. Some of these indicators, deeper karstification ways, ascending type springs, slow drainage during recessions, slow velocity under tracing tests, large currents presence, etc. Several successful regulation projects were done in Serbia. Some of them in some case, Gali-Basera project is in connection with controlling groundwater from karst. Here is some photo. Our colleague was involved in this project. New intake from Montenegro coast. Sub-location spring Bolje Sestre. Pipeline 140 kilometer. The system is for water supply cost in Montenegro. Capacity is 1.3 cubic meter per second, etc. Here's some photo of this specific intake, some photo of, and the last slide is Albania-Italian water deal proposal. The Bistrica Springs, the largest in Albania. Drainage average is around 80.4, and the plan is that with pipeline from Albania to South Italy, we hope actually, Italian hope that they will use that water from Albania for their water supply. Thank you for attention.